Let's talk about wedges now. They're used as structural components. So how well do they work? How do we analyze their holding force? An example below is how much force might be needed to push in the wedge. We're just going to look at the setup of the problem. We know the weight and we know the angle of the wedge. Those are our known quantities. You have 7 unknowns. The P, the force to push it in, and the friction forces, F1, F2, and F3, and the normal forces, N1, N2, and N3. We have 4 equations for these two bodies. We analyze it a lot like a frame or a machine. We look at the free body diagram for this one, and the free body diagram for this one, and the point of contact between the two, F2 on the wedge is equal and opposite to F2 on the block, and N2 on the block is equal and opposite to N2 on the wedge, just like a frame or a machine. And when you combine these two, then you'll notice that the F2s and the N2s will cancel out. If you're considering the free body diagram of the whole thing, N2 and F2 would be internal forces. So 7 unknowns, 4 equilibrium equations, 2 force equations, 1 for each block, so that's 4 equations, and then 3 friction equations, 1 for F1 and 1 for F2 and then 1 for F3. Okay, now for this problem you don't need to consider moment. For the next problem you do. So every time something happens, you get a curveball thrown at you. And the question here is, in this example, is what is the force needed to pull out the wedge? And we consider this block and coefficient of friction 0.3, and what's the force needed to pull it out? Now, we consider the free body diagram of big block and the wedge individually. What is NC? Gee, do we know NC? We can get to it pretty easily. So NA, we can consider everything. We can consider the free body diagram of the big object. And we have 4905 pulling down. That's the weight. And it's acting at 0.5 newtons, or 0.5 meters, excuse me. Now, we've worked out these problems before. Half this, 2452 and a half newtons. And NC then would also equal 2452 and a half. Okay. And I'm just going to do a guess and check. Well, the sum of these two has to equal 4905. Check. No horizontal forces to consider. Moment about the center of mass was pretty obvious. 2452 and a half times a half. 1 clockwise, 2452 and a half times a half meter. Counterclockwise sums to 0. So we're pretty sure we know it. This is fine. Sometimes in these examples in the book, they skip over some steps. They're going fast. This is one step they skip over. Okay, so thinking about this one up here, we're going to have to look at the moments. we'll look at the moment around point A eventually. I just want to get some things set up first. So we have a lever arm going along here of 1 meter, and it's at 7 degrees. So when we look at moments about point A, we're going to have this lever arm times this force times 7 degrees. We're also going to have this times a half. That's pretty easy. We're going to have NB cosine of 7 times 1. So they're the lever arm and the force. Well, I'm just taking the perpendicular force. And the parallel force you don't have to worry about because its line of action goes right through A. This is the only one. We really have to use lever arm times force times the sine of the angle to get the moment. And then we'll go on to consider the wedge itself. So let's take a look at the next step. So moment about A, the weight times half a meter, where the center of mass is, check. The normal force, normal to the lever arm times 1 meter, that's the second term here, check. We got that. We discussed that in the previous slide. This is the tricky one. The friction force, 0.3 is the coefficient of friction, by the way, times the lever arm times the sine of the angle between them. Check. The only thing we don't know is NB. Everything else we do know, so we can just, there's the calculation for NB. 2383.1. Now we go to the wedge. Force in the y direction. So we'll have to go back and take a look at this. Let's think about it. In the y direction, so we have N3 acting up. That's why we needed this number earlier. NB, that's the 2383 cosine 7 degrees, acting down. We will have a 0.3 NB sine 7 degrees, acting down also. See, acting down, acting down. Those are the only three forces, these three here are the only three forces giving us a vertical component. So let's see what the equation says. NC acting up. This would be NB cosine 7 degrees acting down. And this would be the friction force acting down sine 7 degrees. So from that we can get NC. I already did NC. I think there was an easier way to get NC by considering the wedge and the block as a total system. I think this is the long way. I think the way I did it originally was the short way. Okay, next we take a look at the x direction forces. So we're going to get 0.3 NB cosine 7 degrees, and I'm going to write it up here. And that is going to be in the negative direction. And then we have an NB sine 7 degrees. And that's in the y direction. And then we're going to have a P. That's also in the y direction. And those are the only three components in the y direction. From which we can, now that we know NB, 2383.1 I believe it is, we can calculate P. There's NB, we know that. Now, 2383 sine, that would have been NB sine 7 degrees in the positive direction, plus P is in the positive direction, coefficient of friction times NB cosine 7 degrees. So that's how much that is. And I forgot one term. Coefficient of friction times NC. Earlier I forgot one. So yes, I forgot this one down here. I counted 1, 2, 3. I forgot this. So got to add one more. And it's going to be opposing the motion. So it's going to be going in the negative x direction. Yeah, there it is. Now the sum of these four equals 0. 0.3 NB cosine 7, NB sine, P, and 0.3 NC. 0.3 NB cosine 7, NB sine, P, and 0.3 NC. And then solve for P. Everything is known. Solve for P. This is NB. This is NC. NB here. Okay, and we get this answer. It takes a positive force to pull it out. The wedge would just stay in place all by its lonesome if that force equaled 0. If the force is less than 0, that means the wedge would pop out all by its lonesome. Okay, and this is at impending slip. P at impending slip. So it does satisfy FB equals mu S NB, FC equals mu S NC at those 2 points. We still don't know A. We don't know if when we pull out the wedge, is the block going to slide right off over here? That's a question which this example in the book doesn't answer. Doesn't ask, doesn't answer. So, there it is. Assume that the stone does not slip at A. Okay, next problem, next video.